We now want to look at basic circuit elements. Now, let me zoom in here. Now, the basic passive elements that we'll be looking at in this class are going to be the resistor and the capacitor and the inductor. And I'm just going to present them all together because those are the three, but then we're going to leave the inductor and capacitor aside and not come back to them probably until week 7 or so of the class. So I have here a box element, okay, with a voltage entering the left side and a voltage potential across that element. And I have defined, as we've seen before with units, that if we look at the power that is being delivered to that element, we could compute that as P times the V times I, okay? Now, this will be true for all of those three elements. In fact, any element. We'll look at some other elements that are like a nonlinear element, like a diode, an LED. We'll look at other elements that do not behave at all like the resistor, capacitor, or inductor, but they still have a current flowing into them or through them and a voltage across them, and we can still define the power delivered to them as V times I. The thing that's going to be different in each case is what is the relationship between the V and the I. We call these the terminal characteristics. Okay, so the terminals are, either end of this element. Those are the terminals, the leads. And the two things that we can characterize or we can talk about are the current through the terminal, through the element, and the voltage across it. What is the relationship between those two? And what defines a resistor then is an element that if you apply a voltage across it, so here's voltage, and here's, I'm going to plot current versus voltage. If I apply a voltage across this element right here, and I measure the current and I get some current, and if I do this again but for a different voltage, a higher voltage, and I get a new current response, and it's this point, and I continue doing that, eventually I will find that all those points lie on a straight line. And that's what's characteristic of a resistor as opposed to a capacitor or an inductor or any other element. The voltage and the current are proportional, and the constant proportionality ends up being the resistance related to the resistance of the element. So in this case, because I'm plotting current vertical and voltage horizontally, the slope is going to be the delta I over delta V. And as we saw from units earlier, the unit of conductivity is amps per volt. And so that slope actually turns out to be conductivity. Conductivity, which has the units amps per volt, Siemens or mhos. And so we would say I is equal to G times V, or we could flip this around and we could write V is equal to R times I, where R is the resistivity, or is the resistance, and of course R is equal to 1 over G. They are reciprocals of each other. So R equal to 10 ohms means that if we have a resistance that's 10 ohms, it would have a conductivity or a conductance of 1/10 of a mho. Okay? So that's really all there is to a resistor. What else should I say? The power. We want to look at a little bit about the power going into a resistor. So we already know, and you can do the units check on this, that power is equal to volts times amps. Okay, so if you know the current through an element and you know the voltage across it, what effort it takes to push that much current, then you can calculate the power. Now, we can leave it in that form, but because we now have the VI, or terminal characteristics of the resistor, we can replace V with R times I from our Ohm's law, and we get R equals I squared, or R times I squared. We could also go back to V times I and we could replace I here with G times V. And when we do that, we end up with V, or G times V squared. So in the end, power delivered to a resistor is voltage across that resistor times current through that resistor. It's also equal to V squared over R, and it's also equal to I squared times R. Those are all equivalent. And notice that the power is always positive. There's no way you will ever get any power, even for a split second, out of a resistor. It only absorbs energy. It's a hog, okay? So it can never supply power. Now that is, as we'll see, is going to be different than what is true for capacitors or inductors. Now here I have another analogy which might help you in thinking about resistance. So here it's a fluid analogy. So imagine you have a pipe and there's a pressure drop. There's some pressure that you apply at one end. Say the other end could just be open to atmospheric pressure, right? So you just have a spigot, water's flowing out the other end. So if I apply 10 pounds per square inch at one end of the pipe and the other end is at 0 psi atmospheric, then the pressure drop across that pipe is 10 psi, and that will drive some amount of flow through that pipe. The lower the resistance of the pipe, the more gallons per minute or cubic feet per minute or kilograms per minute, whatever that I would get, whatever the flow rate is, okay? And so that's very analogous to a resistance. A real pipe or in real fluid systems, although we might say roughly that the flow rate, that's like the current, is proportional to the pressure drop. In fluid systems, that very quickly becomes nonlinear and not a nice proportional relationship, but in certain constrained conditions that is true, and so that works as an analog to to resistance and electric current. Okay, briefly we're going to talk about capacitors and inductance just to get you primed on, for one, appreciating the difference fundamentally between a capacitor and a resistor, an inductor and a resistor, and then kind of just setting the groundwork for when we dive into capacitors later. So this is the symbol for capacitor. Again, we have current flowing into the capacitor, or through it, but from the left with the polarity plus the minus. And the constituent, that's another term I haven't used, but the constituent or terminal characteristic, the constituent relationship for a capacitor, or terminal characteristics for a capacitor, i.e. the relationship between terminal current, terminal voltage, is as follows. The current and voltage are not proportional. Instead, the current and the derivative of the voltage are proportional. Okay? Current and the derivative of voltage are proportional. And so now the analogy would be, one analogy would be a tank of a fluid. Okay, so here I have a tank. I've put some fluid in here. There's a height h, and there is some flow. If I'm actually putting, in this case, I'm going to put in some flow rate. I'm pushing fluid into that tank, and I am watching the height of that fluid go up. And I think you would agree with me, without having to do really any physics other than just thinking intuitively in our heads from what we know of basic physics, that the rate at which the water height will rise is going to be proportional to the flow rate, right? So if I double how the gallons per minute I'm putting in, I'm going to double the rate at which h goes up, right? And we can actually make this an equality if we put in some constant. Here I put this constant c. So here we're saying that the rate at which the height of the water in the tank rises is equal to the flow rate divided by what I'm going to call the tank capacitance. Okay, it's capacity. And that is going to be related to the ultimately the surface, the cross-sectional area of this tank. We won't go into that, okay? But if you look at this relationship here, and the relationship the constituent relationship that I stated here for the capacitor, do you see the similarity? They're flipped from left to right, but you get the rate at which the voltage across the capacitor rises is equal to the current flowing through the capacitor divided by capacitance. Okay, so the analog is height is analogous to the voltage across the capacitor, and the fluid rate, flow rate going into the tank is analogous to the current that's flowing through the capacitor. Okay, another analogy is the spring. So I leave that here. I'm not going to talk about that. I don't take any time here, but you can look at these notes afterwards and think about it. I've shown that there is a similar relationship here between force, velocity. Okay, dF dt would be like the dVc dt or dH dt, and velocity is analogous to current or to flow. So we'll leave that for now. And let's lastly talk briefly about inductance. Okay. All right, so for an inductor, here's the symbol for an inductor, a little squiggly kind of loop-de-loop guy. Again, we have current and voltage terminal definitions there. And just to review, for the resistor, we had I was proportional to voltage. For the capacitor, we had I was proportional to the derivative of voltage. And we're going to find, I don't know if I write it on here, but if you take the relationship for inductance is, terminal relationship for inductance is I is going to be equal to 1 over L, the integral of voltage. Okay, so you kind of fills out the different permutations here, or different options. You have the current is proportional to the voltage, the current is proportional to the derivative of the voltage, and the current is proportional to the integral of the voltage. Okay, so between those three elements, we have those three scenarios. Now the inductance is measured in henries, as I mentioned, and to explain inductance, we're going to think of a mass. Okay, a mass, and a mass. For a mass, we would say, first of all, we say F equals ma, no problem. We would replace that and say F is equal to the mass times the time rate of change of velocity. Okay, so if I move that over here, see F equals m, it's just ma, but F equals m dv dt, where v is velocity. I'm doing VEL to distinguish from V for volts. Then I rewrite the constituent relationship for the inductor, which is these are equivalent, right? I can write I is proportional to the integral of the voltage. I can then also write that the voltage is proportional to the derivative of I, and that's what I've done here for the inductor. So here we see the voltage of the inductor is equal to L times DIL dt. And you see these are totally the same, exactly the same form, right? Volts is to force as current is to velocity. So coulombs per second, meters per second. You'll see this throughout. These analogs are really, really awesome. So the takeaway here, I just want to end with this, is that the spring. So mechanically, a spring, if I said, does a spring store potential or kinetic energy? I think you would say, oh, it stores potential energy, right? A mass, does a mass store potential or kinetic energy? You might say, well, that depends. We talked about the bowling ball. If the bowling ball is at some height and we have gravitational gravity working, then we can store potential energy in mass. But everything I've been talking about here in the context of the analogs of resistance, capacitance, inductance, let's assume that there's no gravity. Okay, so if there is no gravity, that external gravitational force, then in that case, the only kind of energy that you would store in a mass is going to be kinetic energy. All right, 1/2 mv squared, right, 1/2 mv squared, and velocity squared, or 1/2 kx squared. Okay, and just to put you at ease here, that these things are really very similar. in the electric domain, the capacitor is like the spring. It stores potential energy, and guess what? The energy that is stored is 1/2 C voltage squared. All right, and the inductor stores kinetic energy, so it's like charge in motion. It's just like a mass that's in motion. So there, it's 1/2 Li squared, just like it was 1/2 mv squared. So the last thing to point out, you remember that in physics, when you put a mass and a spring together, okay, put it on a table, and if you extend the spring, so you're giving it some initial potential energy, you release the mass, and let's assume for a second there's no frictional losses. That mass and that spring oscillate. They interact and they oscillate with a periodic fashion. And if there's no losses, then it would go on forever, right? But in reality, there's always loss of some drag, whether it's the air or the surface of the table, and the whole thing decays. Well, guess what? Electrically, the exact same thing happens. You put a capacitor and an inductor together in a circuit like this, and if there is no resistance, no loss in that circuit, which physically you can't have, but you can come close, and you give some initial condition, either energy as a voltage in potential energy as a voltage across the capacitor, or kinetic energy as current flowing through the inductor. You let this thing go, it will oscillate. And of course, it'll decay if there's loss in there. So the analogs between these domains are so similar that it turns out that the math that will develop to solve these systems are totally transferred from one domain to the next. And so that's why I like pointing out these analogs. So anyway, hopefully that gives you a few things to think about as you're trying to wrap your mind around some of these elusive electrical concepts. It is difficult at first, but I can guarantee you that by the end of the course, or well into the course, there'll be a time and time again, students come. I hear students talking later in a subsequent course where we're doing more mechanical things. They actually like to go back to an electrical analog because they feel more comfortable with the electric, and they would have never said that at the beginning of this course. So that's one of the fun things that you can look forward to, is just becoming really comfortable to work in the electrical domain, and even use that as a way to try to improve or increase your understanding of other analog systems that are in non-electrical domains.